It's Mr. Gritto again, ready to close up Unit 4 on the periodic table. So the last thing we're talking about in this unit is what's known as isoelectronic series. And instead of just first ionization energy, what second ionization energy, third and fourth ionization energy all mean. Alright. With these two terms, we want to figure out how atomic radius is going to end up changing. So we have this set pattern where atomic radius increases going down a column or group or family and decreases going across a row or period. When you form ions, your radius changes a lot, and there's just two quick trends with that. Alright, so let's see. So, first term, isoelectronic series. The way I remember this definition is I break it down. Iso is a prefix for stain. Just remember way back when isotope was elements of the same element with different masses. Isoelectronic is going to be same electronic number of electrons. Alright. So an isoelectronic series is a group of elements that all have the same number of electrons. So when ions form, they'll all have the same number of electrons. If we remember, there's a group or family that all elements kind of move towards. They all want to have the same number of electrons as. And that group and family is the noble gases, right? So here, if you look at our example of a of an isoelectronic series, we can see we have the noble gas helium up here with 2 electrons. All 5 of these elements, boron with a positive, or the boron ion, the beryllium ion, the hydrogen ion, the lithium ion, they all have 2 electrons, just like helium. So hydrogen normally has 1 electron, it gained 1 electron, gained 1 negative charge. It became just like helium. Right, they all have 2 electrons. Now, what's cool about elements in an isoelectronic series, although they started out with different numbers or different electron configurations, once they have the same number of electrons, so this is another example of an isoelectronic series, they're going to have the same number of, or once they have the same number of electrons, they're going to have the same electron configurations. So here we can see the electron configuration for each one of these ions and atoms alike are exactly the same. Quick mental bonus. Which one of these elements is a cation? That would be sodium and magnesium. If you said either of those, you would be correct because they are both positive. Alright, so there is a trend that follows along with an isoelectronic series for how atomic radius changes. So remember, atomic radius is how big an atom is. So there's one way to find it that we talked about too. So if we look at this, we can see the centers, 8 plus, 9 plus, 10 plus, 11 plus, 12 plus, that's the number of protons, 8 protons, 9 protons, 12 protons, is increasing going from left to right. But as the number of protons increases, the size is getting smaller. And that's the trend for isoelectronic series that we kind of want to focus on here. As your number of protons increase, it looks like your atomic radius is decreasing. Let's talk about why that is. If you remember atomic radius, there's 2 reasons it changed. 1, going down, you're adding energy levels, and 2, going across, you're having that increased nuclear charge, so it's making it smaller. The one that's going to affect these guys is going to be the nuclear charge. Technically, each of these elements, since they have the same electron configuration, are going to have the same number of energy levels. So these guys all have, 2 energy levels. The first and second, so their outermost electrons are in the second energy level. They all have different nuclear charges though. They all have different numbers of protons in the nucleus. The more protons you have, the stronger the magnet, and therefore the smaller the atom. So if I ever give you a random series like this guy right here, beryllium all the way to lithium, boron all the way to lithium, whichever one has the most protons is going to be the smallest. Try to figure out which one of these guys has the most protons? You can look at your periodic table. If you said beryllium, you would be incorrect. It's actually boron. So boron has 5 protons. It would end up being the smallest in this isoelectronic series, right? Because it has the most, followed by beryllium, lithium, helium, hydrogen being the biggest, right? The general trend with your ions, oh, that's on the last series. The general trend with your ions is as you add electrons, the more electrons you add, the bigger you become. The more electrons you take away, like how these guys lost 2 and 3 electrons respectively, the smaller you become. It's your general trend you can see in your periodic table. Ooh. Where is it? So it's all about nuclear charge. That's why it's decreasing as you go across. Alright, now, the second topic we want to talk about was the different ionization energies. So, you have the first ionization energy, which is the energy to remove 1 electron. You also have the second ionization energy, the third ionization energy, the fourth ionization energy, and so on and so forth. And that's how much energy you need to remove a second electron, or a third electron, or a fourth electron, respectively. All right, so second ionization energy, how much energy does it take to remove a second electron? The key idea here is going to be our elements that are stable are the noble gases. If you try to remove an electron from a noble gas, it's going to take a lot of energy. Right? And let's look at that. So have your periodic table handy. We can go through this together. Look up sodium. So sodium is in group 1, the alkali metals, and its atomic number is 11. Now, we know sodium will end up forming a positive 1 charge because it likes to lose 1 electron. So that's its first ionization energy. It doesn't want this thing, so it has a very low ionization energy, the first ionization energy you can see. So it wants to lose that electron so it can become like neon. Now once it's like neon, the ionization energy jumps up a lot. Check this out. We went from only needing about 500 joules of energy to 4,500. That's like almost like 9 times as much. You need 9 times as much energy to remove the second electron compared to the first electron. Then the other one, it kind of goes by 150%, another 150-ish%. So this one goes up by 900%. This one only 1.5%. So the energy to remove that electron when it's like neon, when it has 10 electrons, is going to be very high. That's what this little box kind of shows you. So magnesium has 12 protons. So if it removes 2 electrons, then it's just like neon. And if you can see this also, it takes a lot of energy to remove that electron that makes it look like neon. So it went from 1400 to 7700, like a 5 times increase, 500% increase in energy. It's a lot. Where this is only, again, like 1.3% increase. Alright, and that's going to be your key idea with successive ionization energies as you increase the number of electrons you're pulling off. It's always constantly increasing. It's always harder to pull it off. But there's going to be a bigger jump when the atoms look like a noble gas, when they have the same number of electrons as a noble gas. Right? So phosphorus, with its 15 electrons, you can pull off all 5 of the first electrons with like maybe a 200% increase max. So this isn't even 200% from the third to the fourth. But as soon as you try to take off its 6th electron, when it has 10 electrons, what is that, triples? More than triples its energy, more than 300%. Well, it jumps all the way up to 21,000 units of energy. All right. So, in general, it's always harder to pull off another electron. We saw that over here. It's always, these numbers are always increasing. But it's always much harder to remove it when the element looks like a noble gas. Right? And when elements have the same electron configuration, the same number of electrons as a noble gas, That's following what's known as the octet rule. It's going to be a big preview into the next unit we're going to talk about with bonding. Alright, that's all, guys. Summarize your idea about how atomic radius and ionization energy relate to the octet rule, and you're good for Unit 4. You've learned all I want you to about the periodic table. Until next unit, of course. Have a good night, Mr. Greto.